And there is an invited talk by Dr. K.P. Mohnan on the topic of integrating mathematics, science and philosophy. Professor Mohnan is PhD in linguistics from MIT, Cambridge. At present, he is with Indian Institute of Science, Education and Research, IISER, Pune, India, in January 2011. He has made significant contributions to linguistic theory in the areas of phonology, syntax and morphology. His academic interests go beyond linguistics to include scientific inquiry and the nature of academic knowledge and rational inquiry in general against the broader backdrop of human belief. He is also an ardent spokesman for radical educational reform. His current preoccupation is to develop systems and resources materials that go beyond the traditional aims of understanding and application of knowledge. As the founding member of Think, a team of educators committed to promoting inquiry and integration in primary, secondary and tertiary education. His mission is to help instruction, set up and conduct courses on inquiry and integration with the hope of helping learners understand the evidence and arguments for against knowledge claims, develop the capacity for critical thinking and ability to inquire, and help an integrated understanding of concepts of knowledge and inquiry. Now I request Dr. K.P. Mohnan to start his talk. Sir, please.
Shifting the educational goals in mathematics and also along with that in other subjects. Traditionally, mathematics in schools would mean teaching students certain mechanical procedures such as addition, multiplication, various kinds of procedures, such that students can execute them very fast. And the ultimate goal is, by the time you come to entrance examinations, you should be able to answer a multiple choice question in 2 minutes. That means you have time to read the question, you have time to think and tick the right answer. Essentially, it means you should not think. That's the whole aim of education that we have inherited. And of course, in the course of doing this, we have to memorize certain formulating equations. What I want to do is to change that idea of education from acquiring certain mechanical skills and memorizing certain things to helping students develop certain capabilities for thinking and reasoning that are characteristic of each subject. So mathematics lends itself to certain ways of thinking. This is very similar to what Professor Rana was saying. Certain ways of thinking and reasoning. Physics lends itself to certain ways of thinking and reasoning. Biology does, history does, philosophy does. So if we can put together all these ways of thinking, reasoning and inquiring, the overemphasis on mechanical procedures that do not require thinking and remembering bits of information that students do not understand will come down. Of course, we need to coach our students to this is not what I've seen here, I guess. To pass the examinations. Okay. This one. Okay, this is. We do need to coach our students to do well in exams, but that has to be taken separately. But along with coaching, we can also help them become educated. That's the central point of the talk. And what I would like to do is to give examples of some of the things that we do in the classroom to achieve that goal. And the examples that I'm going to use now will be very similar in some sense to some of the examples that Professor Rana used when he asked questions like, how do you define negative number? And what are the consequences of those definitions? So let me begin with this. Let's ask the question, what are parallel lines? How do you define them? And if I tell you that line C is perpendicular to both lines A and B. One possible definition from this would be that two lines are parallel if and only if there is another line C that is perpendicular to both. All right? So this looks like a fairly reasonable definition. And because of that, it's clear that it is true here. So let's ask, what are the consequences of saying yes to this definition? What are the logical consequences? So let's take two lines, D and E. You draw a line through the center of both, and that line is perpendicular to both D and E. So it follows from our definition that D and E are parallel lines. Yeah, D and E are both circles. The way it looks now, it looks like ellipses, but yeah.
You said lines, so
Yes. Lines. Yeah, D and E are circular lines.
circular lines.
Yeah, not circular discs. Yeah.
Right.
These are one-dimensional objects.
Right.
Yeah. Okay. So the question would be, if you accept the definition, then you have to accept the logical consequence that D and E are also parallel lines. So, are you willing to accept the definition as a question? Sorry, are you willing to accept the logical consequence? And not only that, if you do that, you get a conjecture, which you can prove easily, that any two circles, by which I mean any two circular lines, are parallel. If you feel uncomfortable about that, notice that this is simply, if you define it that way, you cannot avoid the theorem. Okay? The question would be, is this theorem useful? Is it interesting? Do you want that consequence? That's the question. You might say, no, I don't want that theorem to happen. In which case, you have to go back to the definition and change the definition. So when I do this in the classroom, students don't like this consequence. They say, no, that's not my intuition of parallel lines. My response would be, it doesn't matter. It's simply a logical consequence of beginning with a certain definition. But you can, of course, you are free to change the definition if you want. So, you could take a different definition. So two lines are parallel if and only if they are equidistant. Now you have to ask the question, what does it mean to say equidistant? But let's go by the intuition of equidistance for now. And by that definition, you would agree that this picture, the two circular lines are not parallel. So we have escaped the problem of saying that any two circles are parallel. According to this definition, that's not true. Right? What I'm trying to do is to go through the logical consequences of definitions, changing the definition, and then see what happens. So, now you have a figure in which we have two concentric circles. The circles are distorted a little bit in the moving from one computer to another. But look at them as circles. These are equidistant circles. Yeah.
Sir, I think we are not mentioning one point. The lines are in the same plane, sir.
Yes. We are thinking about two-dimensional geometry, yeah. And flat, two-dimensional flat geometry, Euclidean two-dimensional
All
geometry.
these things are in the context of only planes.
Sorry?
In the context of planes we are talking.
Yeah.
Not in
Plane geometry, yeah. At this point. Yeah. If you move on to curve geometry, then you get, non-flat geometry, other consequences follow. We'll talk about those as well. Now, you would agree that according to the second definition, concentric circles are parallel lines because they're equidistant. And there is, you can prove this theorem that any two concentric circles are parallel. Again, if this logical consequence is pointed out, a theorem is a logical consequence of the conjectures and definitions, the axioms and definitions of a theory. Then students don't feel like referring to these as parallel lines. Again, For math, it doesn't matter what their subjective feelings are. But suppose you say, I don't want that kind of mathematics, I want a different mathematics. Fine, fair enough. So they can experiment by changing the definition. And when this is also pointed out, students say, okay, let's try complicating the definition a little bit and say, we take the first definition, add straight line. For two lines to be parallel, there have to be straight lines. Then this will work. This is a variant of the first definition. And you can also try a variant of the second definition, equidistant straight lines, according to which those circles will not be examples of parallel lines. And you could also consider other definitions. Two lines are parallel if and only if they are straight lines which cannot meet when extended in either direction. And you could say two lines are parallel if and only if they are straight lines with the same slope. Now you can set students to work on these different definitions and they should find out what kinds of logical consequences you get by choosing these different definitions. What we are trying to do is to simply do precise, rigorous reasoning, which mathematics allows us to do. In the first definition, we said two lines are parallel if and only if there is another line that is perpendicular to it. Yes?
As we know, line has no specific length, but when you give a logical consequence, when you take a circle, it has a specific length. So can we say that it is a line?
You were asking me the question, what is a line? Right? That's exactly the question that I want students to ask. That's what I'm coming to. So at this point, we assumed we know what a line means. We assume that we know what distance means. So the next step in this kind of inquiry will be asking precisely those questions. And at some point, we'll discover that we don't know what a line is. Okay, which is a good result. At least it will get students to think about these questions. But the beginning will be some kind of intuition about lines. And many people have this intuition that line means straight line. In some textbooks, that is how it is written. Okay, so
basically line and straight line is the lower classes.
yeah.
We should wait for up
Yeah.
to the completion of the talk. After that, you can ask a question.
So we use the word perpendicular in the first definition. Even in the modified definition, straight line, we use the word perpendicular. What does that mean? So when asked this question, two lines are perpendicular to each other if they are at right angles, is what my students tell me typically. But then the question would be, what do you mean by right angle? Okay? This is interesting because when I ask students what a right angle is, they said, tell me 90 degrees. Now 90 degrees is a way of measuring. And if you look, if you examine the concept of Euclidean mathematics very carefully, lines are things that you cannot see because lines have no breadth, zero breadth. Anything with zero breadth is invisible. You cannot measure with a protractor whether it is 90 degrees or not. That is not mathematics. And number one. Number two, had it been the case that Napoleon won the battle, the answer would be not 90 degrees but 25 degrees. Because Napoleon wanted a complete rotation to be not 360 degrees but 100 degrees. If complete rotation is 100 degrees, right angle is 25. So 90 degrees is just an arbitrary number which has nothing to do with really about mathematics. It is useful for science but not for mathematics. Okay, so the question will be, can you define right angle without using these numbers, without appealing to measurement in mathematics? And students do figure out how to do that. They'll say something like, if two lines meet, if the two angles are equal, then they are right angles. Of course, that leaves the question, what does it mean to say equal and so on? Every definition brings forth other questions. And finally, we come to the questions like, what is a line? what's a point, what's the relation between line and point. At this time, by the time we get to this, students discover they're entering into an extremely abstract world, number one. Number two, a world which allows them to create alternative worlds. So for example, in the Euclidean world, every finite line has an infinite number of points. Well, why don't we change that concept and say every finite line has a finite number of points? So that if one line is longer than the other line, the number of points that the first line has will be greater than that of the second one. That gives you a completely different kind of geometry. And with different kinds of theorems. And we can set the students to discover the theorems in that alternative world. All that you're doing is really changing from the conception of Aristotle's world, where everything is infinitely divisible, to a Democritus world, which when you keep dividing, at some point you stop with the atom. And the atom is a point. One of the things that we have seen in this exercise is that there's a kind of layering effect in mathematics. So we have seen that in this case, when you construct a definition, you use some words, and then the obvious question is, what are those things? So when we define parallel lines, you use the word perpendicular. Then you ask the question, what is perpendicular? And then you create a definition for perpendicular in terms of right angle. Then you ask the question, what is right angle? And then you get things like line, point, and so on. So as you proceed questioning each definition, at some point you reach undefined terms. Because if you insist that every concept must be defined, you end up with concepts which are not definable but left to intuition. And you say, we all know what this means, and we'll proceed with that. That's an important point for students to discover, that when you start questioning definitions, at some point you get to things which are not definable. Okay, and same thing about distance. Distance is a very complicated notion, and it's not easy to define this without circularity in Euclidean geometry. But if you try the other geometry, where every finite line has a finite number of points, it's easy to define length in terms of number of points. You can also ask the question, what's a straight line? Okay, we all think that we know what it means, but fairly easy to demonstrate that we don't know what a straight line is. In fact, I've tried this with students, my students at ISA, and when I raise the question, what's a straight line? Students would look at me and say, why are you asking such silly questions that only primary school students can answer this question? And then 10 minutes you demonstrate that they don't really know what a straight line is. Because every definition that they come up with for a straight line becomes circular, and they get into huge trouble. Because sometimes students say, this is the answer that they give, straight line is one with constant slope. Then you say, what is slope? Then they appeal to the coordinates, so distance and coordinates. But suppose your coordinates are curved. Then will that be a straight line? You're assuming that your coordinates are straight lines, and then defining straight line in terms of straight lines. That's hugely circular. All right? That doesn't work. One definition that we can appeal to, in some cases, would be, sometimes students come up with the idea that a straight line between 2 points is the shortest path between 2 points. That's quite often given in math textbooks, and that we can appeal to. But before we do that, before we get into that one, let me also say, exactly the same kind of layering effect that you found in definitions. If you question one definition, you give another definition. If you question that, you go on, and then you get to a concept that is not definable. Exactly the same way, if you question one theorem, then you prove it with other theorems. Then you question those theorems. Then again you use some other theorems to prove that, and you keep questioning each theorem used in a proof. Ultimately, we get to something that is not provable. just as something that is not definable, you get something that is not provable, you get an axiom. So the grounds, the ultimate grounds that math is built on are really axioms and undefined concepts. That's how you build our knowledge. And if you change your axiom, and if you change your undefined concepts and the definitions, you get very many different worlds. And what's important is to help students construct these imaginary worlds that can be investigated with very precise, rigorous reasoning. That's what math is about. If you do that, students get a very different view of mathematics. Not mathematics as a way of calculating fast without thinking, but mathematics as a way of imagining, a way of thinking carefully, a way of precise reasoning, and creating worlds through their imagination where some of those worlds can be used to model the world that we live in. Mathematics gives us possible worlds, and we use those worlds to model the real world, some of those possible worlds. So, the layering effect that we described is we prove a conjecture by using a theorem, and then you start questioning, you get definitions and axioms, and then when you question definitions, you get undefined concepts. Now, what I've tried to illustrate is the form of mathematical thinking. As I said, shifting from these skills, practice, procedures, etc., to certain ways of reasoning, thinking, and so on. And this, if you look at it mathematics this way, the core of math education then would be helping students to discover and prove conjectures and evaluate the proofs. That's an ability that we can teach secondary school kids. I don't know about primary school. Secondary school, yes. Invent and formulate axioms. These are things that mathematicians do to create abstractions, to define them and evaluate the definitions as I demonstrated just now, and model real life in terms of these inventions. The question to ask is, do we do this? Okay. Most math textbooks that I have seen being used in schools do not. And the result is what I would call strong mathophobia, fear of mathematics among students. A large number of students say, oh, I can't do mathematics, I'm no good at mathematics. And others say, I hate math. These are the two standard reactions that I get. And quite often when a 20-year-old comes and tells me, I hate math, or I'm not good at math, what I try to do is to help them develop certain mathematical abilities, and they enjoy it. All students enjoy it tremendously, but they don't realize that is mathematics. So this is one way of removing the fear of mathematics, or the fear that they cannot do mathematics from a very young age. We will have much fewer mathophobics in schools and colleges if you help them develop mathematical thinking and reasoning as opposed to calculations. So introduce mathematical procedures only after they have developed mathematical thinking. How do you do that? Okay. One way of doing that is to take mathematical thinking outside of mathematics. I will try to finish this in about 40-45 minutes, and so that we have time for discussion. So quite often when I go to a new classroom, I tell my students, my name is such and such, I was born in such and such village, and my maternal grandmother was born when I was 5 years old. Yeah, exactly. So this is the reaction that I get. Students first look at me, huh? And then they start laughing. So I pretend surprised and say, why are you laughing? And some students say, that can't be true. And I say, what do you mean, what can't be true? They say, you cannot be 5 years old when your maternal grandmother was born. And I say, were you there when my grandmother was born? So no. Were you there when I was 5 years old? No. They were not born at that time. So I say, how do you know that then? And they scratch their head and talk to each other and say, nobody can be 5 years old when their maternal grandmother was born. Notice that in order to prove that I wasn't 5 years old when my maternal grandmother was born, which is a statement about me, they say, nobody can be 5 years old when their maternal grandmother was born. So they have a general statement, and from that, it follows that I couldn't be 5 years old. And we work out the proof, the deductive proof on the blackboard. The deductive proof something looks like this. No human can be 5 years old when their maternal grandmother was born. First premise. Second premise, K.P. Mohnan is a human being. And therefore, it follows that K.P. Mohnan couldn't have been 5 years old. And then, of course, I bother them a little bit, say, how do you know that I'm a human being? Okay, this is not provable in terms of mathematics. Okay? So after some questioning, so I could be a robot, a humanoid. I could be an alien looking like a human. They have no way of telling, right? So I say, okay, fine. Take it for granted that I'm a human being. This may not be true, but if you accept this as true, and if you accept the other statement that nobody can be 5 years old when his maternal grandmother was born, then of course the conclusion follows deductively. But then why should I believe you when you say nobody can be 5 years old when his maternal grandmother was born? How do you know that? And the student's reaction is, it's true. I say, yeah, but you believe it is true, I believe it is not true, convince me. Again, this takes a lot of heartache for them. There are two ways of proving it. You can prove it scientifically, and you can prove it mathematically. These two have very different flavors. Mathematical justification and scientific justification have very different modes of reasoning. So I tell them, here is a way of proving it scientifically. You take a random sample of, let's say, 1,000 grandmother-grandchild pairs. It's a random sample of 1,000, and you check their ages. And you'll find that in every case, okay, the grandmother is at least about 20 years older than the grandchild. That is what you find in the sample. So you can now use classical inductive reasoning to say, in this sample, randomly chosen representative sample of human beings, every grandmother was at least 20 years old. Not 20, it's typically, doesn't matter. At least 20 is fine. At least 20 years older than the grandchild. Is true about all humans as well. Now you're moving from the sample to the population. So that's a reasonably good, in fact, that's a standard reasoning in science. But in math, that doesn't work, because how do you know that there doesn't exist some grandmother-grandchild pair in some cave in Africa where the grandmother is younger than the grandchild? You can't tell, right? So you want total certainty in mathematical proofs. And here's the case. If I ask my students, is my heart on the left-hand side or on the right-hand side? They'll say left-hand side. And you ask them, are you completely certain? They'll say yes. Then you point out that there is a situation called situs inversus, where the internal organs are reversed, and 1 out of 16,000 people have heart on the right-hand side. Adult, perfectly normal, in the sense like it is not a defect. So 1 out of 16,000 people have heart on the right. But if you take a random sample of 1,000, you may not find this person with heart on the right. And you might incorrectly conclude that every human being has heart on the left, which would be wrong. For science, it doesn't matter, because science is resigned to uncertainty and fallibility. Math cannot tolerate fallibility. Mathematical proofs have to be completely certain. If the premises are true, it cannot be the case that conclusions are right. Therefore, the standard inductive proof is not admissible in science. How do you prove that for no person can it be the case that she was born sorry, let me rephrase that. No grandmother can be younger than the grandchild. That's their question. Well, for that, what you have to do is to define mother, define grandmother in terms of mother, and then make an axiom about birth. And then if you have these two definitions and the axiom, you can now prove that no grandmother can be older than the grandchild. Sorry, no grandmother can be younger than the grandchild. In proving this, now the grandmother story is not mathematics, obviously. However, it shows a very telling, it's a very telling example of the distinction between scientific proofs and mathematical proofs. Students understand the nature of proofs much better from this example than from standard mathematical proofs, such as, for example, Pythagoras theorem. I remember learning the proof of Pythagoras theorem in high school. I could do it, but I never really understood what it meant. It was only much later, after my PhD, I happened to read Ian Stewart's book on concepts in modern mathematics. I saw a picture, and I looked at it and said, wow, so that is Pythagoras theorem. And then I realized I had never understood it. Even though I could prove it, I didn't understand the proof. I could go through the steps because that's what my teacher said I should do. I did learn mathematics in school and college. No, I don't think I did. I learned what they said was mathematics. But I was uneducated in mathematics throughout my school and college. And I learned mathematics after my PhD in linguistics. I discovered that math is a way of thinking, a way of reasoning, a way of imagining, a way of abstracting. All these things I learned much, much later. But it is possible for us to help our children become truly educated in mathematics if you change our mode of approaching the subject. The goals have to be different. The goal should not be teaching them calculation. Teaching them calculation is necessary, but that's not all there is to mathematics. We can teach them to develop the mathematical thinking abilities that are characteristic of mathematicians. We can teach them what mathematicians do in their professional life. It is possible as long as you keep it simple, keep it at the level where secondary school children can manage. That is a liberating experience. And students who have gone through that experience hunger after mathematics. They start doing mathematics when they're falling asleep, when they're eating their breakfast, and they are riding a bicycle and so on. That's the kind of effect that we want on our children, not simply for mathematics, but also for other subjects. I promised to do this not only for mathematics, but also connected to other subjects. This connection is made in the written version of the paper that you might find in the CD. But let me very briefly say that some of the questions that I raised, what are parallel lines, what's a straight line, what is a line, what is perpendicular, etc. The same kinds of questions can be asked about other concepts. For example, you can ask the question, what is a solid? And demonstrate that physics undergraduate students do not know what it means. If they give you the answer in terms of liquid doesn't have its own shape, but solid has its own shape. If you put a liquid in some container, it takes the shape of the container. You can show that the definition doesn't work. And it's interesting to see the consequences of that. You can ask the question, what's a species in biology? You can ask the question, what is consciousness? What is democracy? What is justice? What is truth? What is knowledge? These are conceptual questions. And so you begin with mathematics, go on to physical sciences, to biological sciences, to mental sciences, to philosophy. Exactly the same strategy of defining and evaluating definitions can run through all these subjects and connect what they learn in one subject to what they learn in some other subject. And this is possible in all these modes of inquiry. What they learn in one subject will be extended to other subjects, such that all subjects are connected together as a kind of integrated web. I don't have the time to show you how that is done, but it will be, if you are interested, you will, let me skip all this stuff. You will find lots of examples of this kind at our website, and here is the address. The address is there again in that, in the written version of this talk, in your CD. So you can go to our website and have a huge bunch of examples, videos, written versions, and so on. So I want to stop here, and so that we have time for questions. That's why I rushed through the last part of the PowerPoint slides.
So now we can have questions. Your hands.
Hello.
A couple of occasions you said that these are kind of use with secondary. What kind of inclusiveness we would suggest for the primary students? What kind of concept they should develop the types of maths and all that? That's a question that I'm facing at home.
Okay. Frank answer, I haven't had the experience of teaching primary school students. My education started with PhD students, went on to undergraduate students, and I started with secondary school students after coming back to India. I have taught 5th graders, one or two classes, but I don't have a feel for what it is like to teach a second grader or first grader. For me, a first grade student is an alien, not a human. So I can't really answer that question until I have taught primary school kids. Here is my guess. I know from neuroscience that certain brain structures that are needed for mathematical abstractions and mathematical thinking appear around the onset of teens, around 11, 12. This is what I know from neuroscience. And this is true about not just mathematics, but other subjects as well. So some of the things that I demonstrated here, which require step-by-step reasoning, may not be accessible to, let us say, 8-year-olds. And on occasional interactions with 8-year-olds, I know that they are not mature enough to do that. So what is it that we can do in primary school? I don't really know, I can only guess. My gut feeling is that if I were to teach mathematics to 5-year-olds or 6-year-olds, I would teach mathematics like scientific inquiry, which is accessible. So students do have some notion of things like circle, triangle, etc. by visual experience, but they don't have the ability to convert that visual sensory experience to an abstraction called triangle. So let's do this, let's do math in terms of scientific inquiry first, which children can do, and then when the appropriate maturity, intellectual maturity sets in, then we move them from the world that we live in to the world of abstraction. This is simply a guess. I'm sorry, I don't know. The answer is actually, I don't know.
Thank you for your answer.
There's one question here, one question there.